The second limitation for the naive Gauss elimination is the division by zero. So in this example, you can see that if the first element here is 0, and if you choose the first equation to be your pivot equation, then you can find the factor f21 to be equal to 4 divided by 0, and you will obtain infinity. So if you further use the factor to eliminate the element here to be 0, so you cannot do that, because when you substitute infinity to the f21 here, you will obtain the solution to be error. To solve this limitation, we can improve it by using the scaling method as well as the pivoting strategy. The function of the scaling is very useful. In the first example here, we use it to standardize the size of the determinant. In the second example here, we will show you we can use the scaling analysis to indicate the requirement of having pivoting or not. The function of the pivoting strategy is to switch the row to avoid the pivot element to be 0 or close to 0. In general, we can improve the naive Gauss elimination by using the pivoting strategy. So we have to perform the scaling to identify whether we need the pivoting or not, to avoid the divide by 0 issue. If we want to solve the unknown x1, x2 by using the Gaussian elimination method, if we look at the pivot element here, is equal to 2. So you thought the pivoting is not necessary because you are not divided by 0. However, this is not true. When you take the scaling, so we divide it by 100,000 here, you obtain this answer, and you get the maximum element to be 1 in the first row. So for the second row, the maximum element is 1, so we don't need to scale the second equation here. So you can see the second row is just remain. In this case, the pivot element is very close to 0, and you have the potential divide by 0 issue. Normally, we always choose the largest element to be the pivot element here. So in this case, the scaling shows that the pivot element is not the largest. As a rule of thumb, if you found that the pivot element is smaller than other row, so you need to perform the pivoting, which means you need to switch the row so that you don't obtain small pivot element here. And we always switch the row that has the largest element. So previously we have the naive Gauss elimination, where we solve this problem without consider the divide by 0 issue. The term naive here indicates the Gaussian elimination without the pivoting strategy. To avoid divide by 0 issue, we need to perform the Gaussian elimination with partial pivoting, which is the GEWPP. In this strategy, we switch the row so that the largest element is the pivot element. This strategy is very important and is the main focus in this study. Previously, from the scaling analysis, we found that the pivot element is not the largest. The largest element occurs at the row 2, therefore we switch the row 2 with the row 1 here. After you switch the row, you obtain the pivot element to be 1, which is the largest element. So this is the partial pivoting strategy. Besides switch the row, we can also switch the row and column. If you do that, you are actually performing the Gauss elimination with complete pivoting. However, the effect is almost the same with the partial pivoting, therefore it's not necessary to perform this step. So the Gauss elimination with complete pivoting is out of scope in this study. Let's continue to solve the previous problem without the scaling and without the partial pivoting. We directly perform the forward elimination to obtain this result, and then use the back substitution to obtain the x2 equal to 1 and x1 equal to 0. And this is the solution by using the naive Gauss elimination. To verify this solution, we substitute inside this formula and check the left hand side and right hand side. If they are equal, then we say this solution is accurate. The left hand side solution is not equal to right hand side solution in this case, and therefore we can say that This solution is poor as it is far away from the actual solution. The high error discrepancy is mainly due to the divide by zero issue, which can be only found by using the scaling. Without the scaling, you might just directly apply the Gaussian elimination, and the solution is very sensitive to the round-off error. So you can see that without the scaling and partial pivoting, you might obtain wrong result. Let's apply the scaling and partial pivoting in the same problem here. So first of all, the maximum element at the system matrix here in the first row must be equal to 1. So to make it 1, we need to divide by 100,000. Therefore, this can be cancelled, equal to 1. This equal to 1. 2 divided by 100,000, you obtain this result. You do not need to scale the second equation, as you can see the maximum element is 1. When we check the system matrix after we perform the scaling, the pivot element here is not the largest. Therefore, we need to perform the partial pivoting by switch the row between them. So switch the row 2 to row 1, and then you obtain this result. And when you check, you found that the pivot element now is the largest. Then we can continue to perform the forward elimination and then perform the back substitution to obtain the x2 equal to 1, x1 equal to 1. To check the accuracy of this solution, we substitute back to the equation here and check the left hand side. So the left hand side is equal to this answer compared to the right hand side here. We see the left hand side is almost equal to the right hand side function. So we can say that this is an accurate solution as it is close to the actual solution. By introducing the scaling and partial pivoting strategy, the solution is less sensitive to the round-off error. Therefore, the solution obtained by the Gaussian elimination with partial pivoting is more accurate than the naive Gaussian elimination.